Hello, this is Dr. Hassan, the engineering doctor, and this is lecture number 47, Shift Registers of Chapter 7, Counters and Registers of the course Digital Logic Design for Digital Systems or Digital Electronics. This slide is a disclaimer for you to read. I cite three references in digital logic design, however, there are many books in the subject. In this lecture, we will cover registers, parallel in, parallel out shift registers, serial in, serial out shift registers, serial in, parallel out shift registers, parallel in, serial out shift registers. We will talk about bidirectional shift registers and the design of universal shift registers. So we'll cover almost all the registers and shift registers in one lecture. It's a very rich lecture. And what are registers? A register is a set of flip-flop in which a binary number can be stored. So a register is a memory element. We can store data in it. We need to store 8-bit or a byte. We need 8 flip-flops to store 8-bit data. And the data can remain there forever as long as the flip-flops connected to a battery or a power supply unit. As the basic function of a register is to hold data within a digital system so as to make it available to the logic elements of the digital system during the computing process. Since a register consists of a finite number of flip-flops, and since a flip-flop can store 1 bit 0 or 1, there is a finite number of 0-1 combinations that can be stored in a register. Each of these combinations is known as the content of the register or the state of the register or n-bit word or n-bit register, where n is the number of bits. As I said, for 8-bit number, okay, so this will be an 8-bit word or 8-bit register, which is a byte in this case. The register could be 16-bit or 16 flip-flop, could be 32 or even 64. Shift registers, on the other hand, registers that are capable of shifting the data to the left or to the right upon the occurrence of a clock pulse are called shift registers. These registers are not normally classified whether they can move the data in one direction or two directions into unidirectional or bidirectional respectively. So if we can move the data in two directions, they are bidirectional. Left to the right or right to the left, okay, they will be unidirectional. To allow the data to be shifted, the output of one flip-flop is connected to the input of the following flip-flop. Very simple concept to allow data to be shifted. Ways to transfer data. There are 4 ways a register can transfer data. Parallel in, parallel out. Serial in, serial out. Parallel in, serial out, and serial in, parallel out, which we will cover them all. Now, for the parallel in, parallel out shift register, the data may be entered by applying parallel data lines to the D flip-flop inputs. It is then available in parallel from the output Q0, Q1, and Q2. So once you have the data on the input and you send one clock pulse, the data will be launched into the flip-flops. How long is they going to remain there? Forever. You can keep the data there and you can use the data as you wish. So this will be a parallel in, parallel out. The data, we feed the data to the Ds of each flip-flop, and you take the output parallel data out from the Qs of the flip-flop, Q0, Q1, Q2, and Q3. Now, serial in, serial out register, we may take the output at Q0 and read the register serially if you apply n clock pulses for n bit word. Note that the shift out clock rate may be greater or smaller than the system original pulse frequency. So we have a serial data n, which is dn, goes to the D flip-flop, to the input to D3. After the first clock pulse, the data comes here. You get, for instance, you are sending 1, the 1 will come at the output of Q3. Now Q3, if it was 0, it will move to Q2. Q2 will move to Q1. and Q1 will move to Q0. Okay, so by doing this, so if I have 1 initially, if I started with all zeros, and I set a single 1, after 1 clock pulse, I will get the 1 here. 2 clock pulses, I will get the 1 here. 3rd clock pulse, you will get the 1 here. The 4th clock pulse, Q0 will have the 1. So you'll get 0, 0, 0, 1. Now, the other clock pulse, you'll take the Q0 out, and the register will reset again. It's a beautiful, simple mechanism that allows you to input the data in series or serial in and take it in serial out as well, serial data out. Serial in, parallel out. The same thing here. If you put the data in series or in serial in, you can have the data as serial out, or you can have it as a parallel out. You can read Q3, Q2, Q1, and Q0 at the same time. You can take them to LEDs to see the data, for instance. Okay? And here also you can apply a clear to clear all the register at any time if you would like to set a new experiment, okay, or test the register for any input data, so you can clear the registers at once by applying a 0. So the flip-flops are cleared by applying a 0 to the clear input, so that every output will set to 0. Parallel in serial out shift register. In parallel in serial out shift register, the data is entered in parallel and comes out serially. Hence, this shift register acts as a parallel to serial converter. Parallel in serial out shift register is also referred to as a special to temporal converter, since a special code is stored in a memory being changed to temporal code time arrangement of bit. So this will allow you really to use this register in many applications. To do that, the parallel and serial out shift register, the data could be applied asynchronously to the shift register. So we have here X will allow you to load and shift the data. So if X is what we need, if X is 1 and the data coming in here is 1. So 1 and 1, you will get a 0. So you will set the preset to 0 and you will move the 1 to the queue. Okay? So X will allow you to load the data. Okay, when X is 0, will allow you to shift the data. If this is 0, and the clear, where this came from? This came from the previous lecture, the 2 NAND gate for the preset and the clear. So you need a 0 to set a 1, and you need a 0 to set a 0. But if both ones, and both will become 1 when X is 0, so the register will act like a shift register. So this data in parallel, and we can get the data out, so asynchronous parallel load, and you can get the data out in serial data out to allow you conversion parallel to serial, or even you can get the data out in parallel if you want to observe the data. This register also allows you to have a serial data in. So you can have a parallel data in, a serial data in, a parallel data out, and a serial data out in one register. And this is, of course, is a shift register which will shift the data from the left to the right, because I'm taking the Q's to the D's here. Do you see? Okay. So very simple, allow you to parallel and serial out data, and we can have a serial in, serial out as well for this register, for parallel in, parallel out at the same time. Now, we can have a synchronous parallel load. Rather than using asynchronous parallel load by using the preset and the clear, I can have DI, I can have a Y control signal. If Y is 1, this will be the shift mode. If Y is 0, if y is 0, this will be the parallel data mode. So di, every di will be y prime, okay, or qi plus 1y. If I need qi plus 1, for instance, if I need for a shift register to work, okay, I need the previous qi plus 1. So the d will have a q3. For instance, if I have d2, if I'm looking at the d2 here, the input, what I need a q3, okay, to be connected to d2. This will do it. d2 will be q3y. If y is 1, d2 will have a q3. So y is 1 will be allow you, will be a shift register, allow you to shift the data from the left to the right. The same thing for d1. If it's d1, I will take q2. Okay, d1 will have a q2 when y is 1. However, when y is 0, we will load the data I2 to d2 and I1 to d1. Okay, so with this simple equation could be implemented with 3 NAND gates or 2 AND gate and OR gate. We are using 3 NAND gates to implement every. For D3, for instance, D3, we don't have Q4 before it, right? So what will this is will be the serial data N, okay? As you see here, serial data N. So II, y prime plus qi plus 1 y, and this will allow you to establish di. Okay, so this is parallel and serial out shift register or synchronous parallel load. The synchronous parallel load. It's very simple. The load is uploaded upon synchronized by the clock cycle when we are not using the preset unclear. Okay. Now, the bidirectional shift register, the data could be shifted with a control signal S, could be shifted from the right to the left or the left to the right by simple equation. So S, if S is 0, I will shift the data to the left. If S is 1, I will shift the data to the right. If S is 0, I will shift it to the left. If S is 1, I will shift it to the right. This is how it will work. DI for D2 to shift the data from the left to the right, D2 has to get Q3. So S needs to be 1. So D2 will be Qi plus 1, and this will be 0. If I am shifting the data, D2 has to get to Q1. If I am shifting the data on the opposite direction, okay, from the right to the left, so D2 will have to have Qi minus 2 minus 1, which is a Q1. Okay, so S has to be equal to 0 because S sublime will be 1, and this will go away. So simple 2 NAND gate and OR or 3 NAND gate circuit to implement this equation for every flip-flop will allow us to design a bidirectional. Again, for D3, we don't have a Q4 for D3 right here. So Q4 will be what? Will be serial input N. And the same thing for D0, when we have D0, we don't have D minus 1. So this input will be serial input for shift left. Again, could be a parallel out. You can get a parallel out. You can get a serial out for shift right, a serial out for shift left, a parallel out, and a parallel in. A beautiful design for bidirectional shift registers. Also, rather than using NAND gates, we can use multiplexers. So the multiplexer, the same thing, based on the select signal. Okay, either we select the Qs Okay, for instance, D3, either we select for D2, let's look at D2, either we select Q3 when the select line is 1, or the Q2 to shift left, okay, or the Q2, so D2 will be either Q1 or the Q3, either the Q3 or the Q1. Q3, if we take a Q3, we are shifting right. If you are taking Q1, we are shifting left. And everything. And here again, we replace it with the serial N and the serial N for shift right and serial N for shift left with the other multiplexer. So this is identical to the previous circuit, just we change the 3 NAND gate to a multiplexer circuit, to a 2-to-1 multiplexer to generate the Ds. So this is again a bidirectional shift register with using multiplexer. Now, to design a universal shift register, which there is an integrated circuit for this, we use two select signals, S1 and S0. And 4 multiplexers, each is 4-to-1. So 4-to-1 multiplexer 0, multiplexer 1, multiplexer 2, multiplexer 3. So if S1, S0, 0, 0, we are in the hold mode. We are in the hold mode. It means the data uploaded will be the queues. See, will be Q3, L0 will be Q3, Q2, Q1, Q0. So the same data in the flip-flop will be uploaded again. So this will be the hold mode. So you don't see any change. If 0, 1, we are shifting what? We are shifting right. Because D3 will get to Q2, and D2 will get to Q1, and D1 will get Q0, and D0 will get the serial input for shift left. Okay, if 1, 0, you will shift left. 1, 0 will shift left. So the D3 will get a serial input, and D2 will get Q3 because we are shifting left. D1 will get Q2, and D0 will get Q1, which is very correct. And parallel load, 1, 1 will be parallel load, so we will have those parallel load, L3 DC, I3, I2, I1, and I0 will have a parallel load. So this is a universal shift register, allow me to do all the operations. Parallel load, parallel data out, serial data out, serial data in for shift right, serial data in for shift left, parallel load, parallel data out and parallel data in, and serial data in and serial data out for both directions, left and right. So this is why we call it a universal shift register. And I thank you very much. Please subscribe by clicking on the blue circle, and hopefully see you soon in the next lecture. Sincerely, Dr. Hassan.